Welcome back to another video in our course on probability theory. Last time we introduced weak convergence, which was a kind of convergence of distributions or measures. And today we are going to dive a bit deeper into this topic and learn about the notion of tightness. This is similar to a notion we already had, which was uniform integrability. And tightness will give us a way to say if there are convergent subsequences of a set. We will then have the so-called Prohorov theorem, which states that a family of probability measures is tight if and only if there are convergent subsequences. So let's get started. With Prohorov's theorem. But before we can come to this, recall vague convergence. Remember from last time we had this. Let me just go back. Weak convergence, Pn converges weakly to P, was if all integrals with respect to f's, which were bounded continuous functions, converge. And for vague convergence, we had the functions which are continuous and have compact support, which is a subset of all these. Which means all weakly convergent sequences are also vaguely convergent, but not the other way around. Okay. So this is just to recall what we just did. And the first result I will present here is if you have a vaguely convergent sequence of probability measures, then the limit is a subprobability measure, which means it has total mass at most 1. So that's important for all we will do today. Let's prove it. Let's take a sequence Fn, which goes up to 1. And the Fn's are, well, have compact support. So that's the real line here. You might choose something like this here. Minus n to n. Do something smooth here or continuous. And that's then Fn. And if n goes to infinity, well, this converges pointwise to 1 in a monotone fashion. And then you have mu of r equals by continuity and by monotone convergence, supremum over all n. You have, well, let's not take n, but let's take another letter here, which is k. Kfk. And that's the same as sup over all k. Lim sup p n f k. N goes to infinity because this limit here, by assumption, okay, assumption is here, vaguely, that's what I wanted to say. Okay, yeah, that just means vague convergence, so this kind of convergence that we just discussed. And this here equals this here. And now, okay, the P and F's, they're less or equal than 1, so the supremum of all these things is also less or equal than 1, and we are done. Yeah, from this we can conclude so-called Helly's theorem. If you have probability measures on R, then you find a subsequence which is vaguely convergent. And I say here, in other words, the space here is compact or sequentially compact, meaning that every sequence has a convergent subsequence. So also here, the sequence here has a convergent subsequence. Excuse me. Let's prove this. So the Pn's have distribution functions which I call Fn. Distribution function of Pn. And then take x1, x2, and so on, a denumeration of a dense subset, for example, Q. Using this, we might choose a sequence nk, k from 1, 2, and so on, and f right continuous with left limits, such that fnk of x goes for k to infinity to f of x for all x in Q. So why can we choose this? So if you fix x, then fn of x, sequence in n, takes values in a compact space 0, 1. And because the space is compact, we can choose a subsequence such that you have convergence. You can do it for every x in a single fashion, yeah. And then what you usually call a diagonal argument gives you this here, that this convergence here holds for all x in Q, since Q is the numerable. So start with x1, choose a sequence here, then pick a subsequence of the first sequence such that fnk of x2 also converges, a further subsequence, and so on. And then you take the diagonal sequence of all these, of this rectangular array, and you get exactly a sequence like this here. Well, now we have the f here. That's very important because this f here gives us a potential limit. Not really, it gives us a potential limit for the distribution function. So we have still to define measure x and y like this here is f of y minus f of x. And now we have the potential limit. And we need to show that Pnf converges to Pn, sorry, not Pnu, that's not how it works, to mu f for all f in CCR. And with a lot of generality, we assume that f is non-negative. Because then we can write the following. The integral of f with respect to mu equals, as we know, the integral from 0 to infinity, mu of f bigger than t dt, because this here is an expectation, and the expectation of non-negative integrals can be computed like this. We had this before in this course. Yes, and now we have this here. F is continuous. F bigger than t must be an open set. That's an open set, exactly. F must also be bounded. It's also a bounded set, actually. F bigger than t. And what we also have this here is, as in the portmanteau theorem, the limit of Pn f bigger than t, Pn f bigger than t, and lemma for 2 tells us that if we plug out the lim_inf, we at most make that bigger. So we have this here. This is apparently the same as lim_inf Pn f by the same argument as in the first equality. This here is less or equal than lim_sup Pn f. And then we can revert everything back. We have the lim_sup here, which is minus lim_inf of Pn minus f. We can do the same argument here and the same argument here with the other direction of the inequality sign. And we get that's less or equal than mu f. And this, since this here is the same as this on both sides, we can conclude that everything must be the same. In particular, that lim_inf equals lim_sup equals mu f, which means vague convergence because f was arbitrary. And we're done here. Okay, that was vague convergence. And this very powerful thing here, Halley's theorem, showing that we have essentially a compact space. So every sequence has a subsequence which converges. Let's come to weak convergence now, and to the notion which I introduced in the beginning, tightness. So as a family is tight if this here holds. So that means, so here it's a bit nicer written down. So K is a compact set, or here K is a compact set, and Pi of K for all compact sets here, some supremum should be 1, but the supremum over all infima. So if you give me the family and you also give me some epsilon, I need to find a compact set K such that all Pi of K's are bigger than 1 minus epsilon. That's how it is. And the same for the distribution of random variables. Here the only thing is xi are called tight if their image measures are tight. Then you have this here. Okay, that's tightness. And you might remember in the measure theory course we had that if E is a Polish space, then all single P's are tight. That was also quite a result, which says that if you have a single probability measure on a Polish space, you find a compact set which carries almost all mass up to some epsilon. Another statement, if E is compact, then of course every family is tight because you can always choose E as the compact set. And if you can use E here, well, Pi of E is always 1, so that's trivial then. Another thing, if you have probability measures which have bounded expectation, then they are tight because, well, so they're real valid now. So you need something like xi bigger or equal than r. So, well, first of all, let me say this here is the same thing as to say the infimum over all sup k I pi of the complement of k equals 0. So just writing 1 minus on both sides here, and putting in the 1 minus and giving the complement instead of this here. So this here means outside of some k, there is uniformly in all I very, very small mass. So here I have this here, P of xi, absolute value is bigger or equal than r, and r is something big. Take infimum over all r, and the supreme over all I. Well, if the assumption here holds that they have finite expectation, I can use Markov's inequality and have P of absolute value of xi divided by r inf sup over all I inf over all r. Well, this supremum here is finite, and if I divide it by r, well, I can divide by a very large number, so this is 0. So these are tight. Then vague convergence and tightness. We saw that vaguely convergent sequences have the property that the limit here is a sub-probability measure. And here I claim that it's a probability measure if and only if the PNs are tight. And in this case, they also converge weakly. So that means tightness means convergence. So for example, as we will then also see, if you have the PNs here, which are tight, then you can first say, well, there is a subsequence which converges vaguely. Then you know if they are tight by this result here, that the limit also has mass 1 and Pn converges to the mu weakly, which means if you have something tight, there is a weakly convergent subsequence. And that's what we are going to use then in Prohorov's theorem. So let's come to this here. First, for any radius, you take a function gr with the following. So br of 0 is more equal than gr equal to indicator br plus 1 of 0, meaning that I have r here. So gr is 1 between minus r and r. It's 0 between left of minus r minus 1 and 0 right of r plus 1. And I just have to find a smooth or continuous version of this, and that's my gr. And of course, I have that Pn n equals 1, 2, and so on is tight. If and only if, well, what we had here was something like this here, subinf pi of k equals 1, or here, that's what I need, inf sub, the complement equals 0. No, I need this bit here, I need, with equals 1 on the right. And there's not a very big difference between integrating against gr and the indicator of br. That means that's tight if and only if supremum over all r lim inf of Pn gr. So this here is approximately as good as evaluating Pn on a compact set K is 1. N goes to infinity. So yeah, apparently that's an equivalent formulation of tightness, because all which happens is that the integral with respect to GR lies somewhere between the mass on BR of 0 and BR plus 1 of 0. Now we have this, and there are two things we have to, or there are actually three things we have to prove. First, from right to left. So if the total mass is 1, then the PNs are tight. And here we have, well, the assumption that's 1. Mu of R is 1, and mu of R, that's also the supremum mu integrated with respect to GR, because the mu measure is finite. And we have continuity from below of these integrals, or maybe that's also monotone convergence or something. This here is, since we have vague convergence, the same as to say supreme overall R lim inf Pn integrated with respect to GR, n goes to infinity. And since everything in here is smaller or equal than 1, then this here is smaller or equal than 1. Which means everything here in this inequality chain must be 1. In particular, this here must be 1, which is, as we just saw, the same as tightness. So we've proved here from right to left. Let's prove also the direction from left to right. So they are tight, and we have to show that the limit has total mass 1. We already know that mu of R is less or equal than 1. This here is, as before, the supreme over all R equals 0, mu integrated with respect to GR. This here is, well, just turning around all arguments, basically. I can just write down here the same. So mu of G, sub mu of GR is like here, that's here. And that's because of the vague convergence, and we have this. And by assumption, we had that the PNs are tight, which is the same as this here equals 1. So I can say, well, that's equal to 1. So that means everything is the same here, in particular mu of R equals 1. And we are done with this. So we still need that the PNs converge weakly to mu. So how does that work? So let f be continuous and bounded. Then we compute Pnf minus mu f, and we have to see that it converges to 0. And the trick is to smuggle in the GRs from before. So Pnf minus FGR plus Pn FGR minus mu FGR plus, well, mu F minus FGR. And we need some absolute values here, like this. And now let's see. Pnf minus FGR, okay. FGR converges uniformly. So that this inequality here holds for all R, of course. Yeah, that holds for all R. So how can we bound all this? So here I can pull out an f, or the largest value of f, which is a bounded value, Pn integrate against 1 minus gr. But this here, as we know, is close to 0 from this here. So this here is small, first term. This here is also small as n goes to infinity. It becomes 0 because f times gr is a function with compact support, because gr has compact support. So the Pn's converge vaguely to mu, which means these integral converge here. So this here converges to 0. And here again, I can bound by the absolute, so the sup of f times mu outside of the box minus rr, which is small. So that means here, like this, as r goes to infinity, well, this here goes away, this here goes away, and well, we still have this here. Limit r goes to infinity, Pn fgr minus mu fgr. And then we can let n go to infinity in order to see that this is 0. And we are done because that's what we wanted to show. Then we're almost done. It only remains to prove the main result of this section. But first of all, another important thing, if Pn's converge weakly, then they are tight. Well, how do we see this? So if they converge weakly, they converge vaguely, as we said. In addition, if they converge weakly, the integral with respect to the one function must also converge, and this means that P here is a probability measure. So I have a vaguely convergent sequence, and the limit is a probability measure. And then, as we see here, the Pn's are tight, which is exactly the claim of this result here. Okay, now let's come to Prohorov's theorem. Let me also say, in the manuscript there is a more general version, which is exactly this here. I'm going to prove the result only in the case that E equals R, because that was also the case for the other results in this video, in particular Heddy's theorem. The more general version is, if you have a complete separable metric space and a family of probability measures, then equivalent R, the family is relatively compact with respect to V convergence, meaning that for every sequence there is a convergent subsequence, and the equivalent is the family is tight. Let me briefly go through this. And a TF is here, not a TF, that's a subsequence. So only for I equals N and equals R. Okay. From left to right, which means from 1 I have to conclude 2. So I have to show something is tight, and yeah. Assume that the sequence here is relatively compact, but is not tight. Then I have to have a contradiction. It's not tight, so there is an epsilon. Such that, since it's not tight, there's epsilon such that for all compact sets, I find one probability measure which has mass epsilon outside of the compact set. And the compact set, without loss of generality, is just a ball around 0. So it's not tight. That means I can find the subsequence Pn of bk of 0 is always bigger than epsilon. So that's by non-tightness. So I can choose a probability measure here in the sequence such that I find mass epsilon outside of this ball here. On the other hand, I have assumed that we have V conversions, so Pn according to P. So, well, I have the following. So where to start? Yeah, I have weak convergence. Pn goes to P. So Pnm of the complement of bk of 0 must converge according to the Portman-Two theorem to this here, which is by assumption something which has mass less than 1. So here k is fixed, and if I make the k to an m here, I make everything at most smaller because the complement is becoming smaller. And this here, by assumption, or this here is bigger than epsilon. So we have epsilon bigger than epsilon, which cannot be. So there's a contradiction, and it just cannot be that we have convergent subsequences but no tightness. Okay, that was from 1 to 2, and then from 2 to 1. How does this work? So the family is tight. So we might choose a vaguely convergent subsequence. Let's take the subsequence. The mu has to have total mass 1. Which means exactly like this here. This here then holds. And I have weak convergence, which means I have found my weakly convergent subsequence. Exactly. And the more general version of Prohorv's theorem is in the manuscript, where ER is a complete and separable metric space, and there the construction is more complex. Nevertheless, that's it for today, and next time we are going to talk about specific limit results. Hope to see you then.